So just want to go back to this, just as a little review. And I was going to bring my university textbook. I wish I had brought it, and I thought about it last night, and then I forgot it this morning. And again, I keep saying to you guys, physics determines this, and unfortunately, that comes across as a lazy teacher answer, right? You guys are asking me some great questions, like how do we know it's 15 billion degrees Celsius in the center of a star? How can you tell that? And I throw out to you the word physics. And I know that seems at this point in your science lives as kind of a cop-out, but it is a complex series of laws that we know that exist in the universe, and all of those laws and calculations go into what we believe to be the temperature at the center, okay? So by bringing the textbook, even though you don't understand the mathematics, by showing it to you, I would hope you'd appreciate that someone has gone to great, effort to write a book on it, and therefore there's been a lot of thought and a lot of theory behind it. So I apologize for just throwing out to you physics, because you guys don't know the rules of the physics. Let me give you a classic example. You guys we've talked about certain forces, right? And the big one that's involved in astronomy is gravity, right? We've talked a lot about gravity, that the force of gravity drops very quickly, and that the force of gravity is what keeps things in orbit. And I think I mentioned it, but I hope I've told you, it's gravity that's pulling all of these gases together, all right? Objects are spheres in the sky, whether it's planets or whether it's a star. They're spheres because the way gravity works is it pulls into that central mass with equal force depending on what the distance is, the radius. So everything's pulling in all directions with the same strength. And when you have that type of pull, it will automatically create a sphere. All right, it'll create a spherical shape. All right. So gravity is what's holding these objects together. Yep. Okay. So we're going to get to talking about larger types of stars. We're eventually going to get to something called black holes, where light can't even escape from that particular type of object. So we'll get to that in a moment. The light is pulled by gravity, all right? But the gravity in the sun's case is not strong enough to keep the light from leaving. So the light is able to escape and get to us, okay? Yep.
So, like, I think you said a little while ago something ran into, like, the Earth.
The Earth?
The moon was created in
yep.
the Earth, like, the gravity made it.
Correct, yes.
How come the mountain isn't shaking? Like,
okay, so again, this doesn't have anything to do with what we're dealing with here, but I'll answer that quickly. In a collision like this large asteroid running into the Earth, it would create massive amounts of heat, like friction. Like if you take a tennis ball, actually, does anybody know what the sport squash is? Have you ever heard of squash? You got a special long racket. It's played in a room, and you bounce it off the walls. And it's got a little ball in there that really isn't very bouncy, right? If you ever had a squash ball and you drop it, it doesn't hardly come back up. But when you start playing the game squash, the ball gets really bouncy. It bounces better. Does anybody know why the ball gets really bouncy after playing a game for a while? Yep. It heats up. It gets hot. The ball gets warm, okay? So when that big asteroid crashed into the Earth, it created a massive amount of heat. We believe that it literally melted some of the Earth's crust into a liquid like magma from a volcano. You know what I mean? It would have maybe taken a chunk out of the Earth's crust, exposing the liquid, which then would be, due to gravity, allowed to flow into a spherical shape. You see what I'm saying there? So that's how they believe those spheres then came about in that case. Plate tectonics, you learn about that in geography. Have you learned about that before? It pushes, so that on the Earth there's these plates that are floating around on the magma that push together and make mountains, right? They're making tall mountains. But as time goes on, erosion is going to erode those mountains. Wind's going to come along with some little rocks in it. And in billions and billions and billions of years, if plate tectonics stop, we would get to a nicer sphere, okay? But we live on a planet that's very active. There's liquid underneath the surface of the crust. Things move around. And so we still have geological formations being produced here. And therefore, we're not to the point in the life cycle of the Earth to have that, you know what I mean, become perfectly round, okay? Talking more about the sun, you might ask the question, if gravity is so great, why doesn't it keep squeezing the sun to a smaller circle? If it's made up of a bunch of gases like hydrogen, why doesn't gravity just keep on pulling things in and getting smaller and smaller? What is stopping the gases from being squished into a tiny little ball? And the answer to that is the energy that's produced inside. The energy that's produced inside is like pumping up a balloon, all right, or blowing up a balloon. The energy that's produced inside creates an outward pushing on the gases. Gravity is pulling it in, and so at some point, there's a balance. The energy of the motion of the particles is pushing out, like the gas in a balloon. Gravity is pulling in. The balloon doesn't have gravity pulling it in. It's the rubber of the balloon that pulls it in, but gravity pulls it in, and it reaches this nice balance, all right? If for some reason the gravity were to win and it started to get smaller and smaller, when you squeeze down on that gas, it actually makes it hotter and hotter. Have you ever pumped up a bicycle with a bicycle pump? Not the cheap move like using a big air compressor. Brrr, yeah, that works great. But have you ever done it with a bicycle pump? What happens to the pump as you pump in the air? What physically happens to it? Yep. It gets harder to push. That's correct. What else happens to it? Yeah. It gets hot. It gets hot. When you squeeze gas together like that, it generates heat. So what happens is, if gravity were to win and the sun were to get smaller, that's going to heat things up on the inside. That's going to make that fusion reaction go faster, sticking more hydrogen atoms together. And if more energy is formed, it's going to push back out on the gravity. So if gravity starts to win, then more energy gets formed, and it pushes it back out to its original size. Let's say for some reason the sun were to get too big. If it were to get too big, then it's going to cool down in the center. It's going to slow down the reaction, and then gravity will win, bring it back to the right size. So there's a balance between gravity and that reaction that produces the heat that turns the hydrogen into helium, and it keeps it a perfect size. So the sun doesn't change in size. It doesn't grow or get smaller because there's a perfect balance in that reaction that makes the energy and gravity, all right? So that's kind of an interesting thing. If the balance were to get out of whack, then the star is going to change size. If the fuel runs out and now that reaction can't happen anymore, then things are going to change, and that's what happens when stars die. And that's what we want to talk about today. All right. So let's move on to today's. And now we've got to talk a little bit about how we categorize stars. Oh, and I had some notes that I wanted. No, I can figure it out. I'm smart. I don't need to look at my notes. At least I think I'm smart. Hold on, let me change that. You guys think I'm smart. Well, some of you think I'm smart. Let me change that. Some of you question that. I know. All right. I want to talk now about brightness. Yes. So we talked about luminosity yesterday. Luminosity is how much energy that star is giving off. Like when you turn on a light bulb, it gives off so much energy. It's measured in watts, just like a light bulb is. I think on yesterday's note, we said that the Earth was something times 10 to the 26th watts. It was 26 because Danson made a connection that had no sense, that had nothing to do with reality. That linked it with iron, which is now, I'm never going to forget that number now because now I think of iron. And we call that one solar luminosity, as if we're saying our sun is a standard bulb, like a regular light bulb, like a standard light bulb. Just to compare, the brightest star in our sky, we'll talk about it later on, it's called Sirius. It has a luminosity of 22 of our sun. So it's like 22 times the amount of energy that's leaving our sun is leaving that particular star. Okay? Now, obviously, when we look at the sun, it looks a lot brighter than that star, even though this star Sirius is giving off 22 times the energy. And the reason is our sun is close to us, and that star is very far away. So I can have a really bright light bulb, but if I take that bright light bulb a kilometer down the road, it's not going to look very bright to me anymore. Okay? So that means here on Earth, when we want to talk about stars and how bright they are, we have to take into account two pieces of information. How much energy is it given off, the luminosity, and how far away it is. And that's true about any light source, right? You can have any bulb, put it close to your eyeball, it's going to be bright. Take it far away, and it's not going to look as bright. But it doesn't change how much energy it's giving off. Two important terms. Magnitude. Magnitude is a term that we use to talk about brightness, how bright it is. The apparent magnitude, how bright an object is, it seems from Earth. We look up in the sky, we see an object, it's got a certain brightness, and we've calculated a number for the magnitude. Now, I'm not going to tell you how to calculate that magnitude. To be honest, I learned that in this course that I took in first-year university. I didn't understand it then, and I still don't understand it now. It is a weird unit system. It's upside down and backwards, for crying out loud. The way it works is, if the number is small, it means it's really bright. It can even have negative numbers. Numbers that are negative, that are so into the negative, they're super bright. If the number is big and positive, then it's dim. It makes no sense. I read up on it the other day because I wanted to make sure I knew what I was talking about. It's a reverse logarithmic scale. I'm like, what? A reverse logarithmic scale? Who thinks of that? I read about the guy who thought of it. I still am not sure why they do it that way. If we look at our sun and we look at the apparent magnitude, I think it's like negative 25 or something. You could check it on Google if you wanted to, the apparent magnitude of the sun. If you look at the moon, it's also negative. But looking at stars, they're positive. And that means they're dim. It's a backward scale, and I don't know why they did it that way.
As the numbers get bigger, they get smaller in size.
You mean like the pellets?
20 gauge, 12, 10. Like they go like 20 is tiny, and 12, 10 is bigger and bigger.
All right, there you go. We'll blame the rednecks.
Negative 26.7.
Is what, the sun?
Yeah.
Negative 26.
But Sirius
Serious?
is negative 1.46.
Right, because it's still bright, but it's not as bright as the sun. So it's a smaller number.
But didn't that just
That's the luminosity. That's how bright it is compared to the bulb. But luminosity is the energy, all right? But now we're taking into account how far it is away. And Sirius is so far away, its brightness is dimmer. You see what I'm saying? Okay? All right. So apparent magnitude is goofy. Absolute magnitude. This is something that's important to us if we want to study stars. Absolute magnitude is how bright an object would be from a set distance. That set distance is 3 parsecs, which is 33 light years. There's a very complex calculation that scientists do to get that, because what they've got to do is they've got to take the apparent magnitude, what we see here on Earth. They've got to make an estimate of how far that thing is away so they can work their way backwards and figure out the luminosity. And then they've got to do another calculation to move it out to a certain distance of 33 light years. So there's a lot of mathematics. The mathematics, the trickiest part is figuring out the distance. How far away is that star? That's an entire another group of lessons that I'm not going to be able to teach you guys. But there are many ingenious ways in which scientists have been able to figure out distances to stars, okay? And we have to do it here on Earth just by looking out there. And so if you want to know that, you'll have to come on by at lunch, and I will have a separate lesson on how to figure out distances, but don't worry about it. Okay. If we want to compare one star to the next star, we look at this absolute magnitude, because it's kind of like we're looking at them at a set distance away so that we can see what they look like from the same distance. Okay. Man, I've been talking for a long time. I didn't say anything, Rachel, because I'm afraid of Rachel. She's turning to the dark side. Everybody see her hood? I mean, she's joining a gang. All right, I'm going to move on. All right. Yep. So absolute magnitude. What are you looking at? The absolute magnitude of what? The sun. So the apparent magnitude is how bright it looks like on Earth. Okay, right? So what's that number for the sun? Yeah, what's the apparent magnitude for the sun? -26. Let's just go with -26. According to that, that means it's really bright. It's negative. It's a negative number. I shouldn't maybe have said small. I should maybe have said negative. Not important though. That's super bright. Okay? Now, we're really close to the sun, right? Now let's imagine that we took the sun and we moved it out to a distance of 33 light years. That's way out there, right? Because right now the sun is at a distance of 8 minutes for light. If we move it way out to 33 light years, it's going to look a lot dimmer, isn't it? What's the absolute magnitude for the sun? 4.83. That's big. And that's because at 33 light years, it's going to look a lot dimmer. That's why the numbers do that. Okay? Does that make sense? Because positive big is dim and big negative is bright. I should have maybe said that. It flanks 0, like a temperature scale. Okay? All right. Okay. Now, if I want to compare one star to another star, talking about what it looks like from the Earth makes no sense. So I've got to talk about the absolute magnitude so that I can talk about how they look from the same distance. Don't write, oh no, I do want the color temperature. Let me just look ahead, life cycle of stars. Okay, when we get to this chart, we're not writing that down. So you can write that down. I thought we were to the chart, but not to the chart yet. All right. Not only when we talk about stars Do we talk about how much energy they can give off? But we also want to talk about how hot they are. Those things are not necessarily linked. Because you can have a big, cool star that doesn't give off a whole lot of energy, but you could have a small, hot star and give off lots of energy. These numbers don't have any meaning. I'm not making you memorize them. You could write them down. But what I do need you to know is cool stars are red. Medium to cool stars are yellow. That's us. Remember? 5,500 degrees Celsius at the surface. Medium to hot stars, they're getting way up there. And super hot stars are blue. They've got temperatures like that at the surface. Yes? It's a continuum. It's a continuum. We could call them yellow-white, turning yellow to white. It's like a rainbow. It's a continuum of colors. So I don't necessarily have all of the temperatures in there. This would be going from white to blue. It'd be a whitey blue. You see what I'm saying? What's that? Pale blue, sure. What I want you to know, though, is that the cool ones are red, yellow, white, blue. That's that same thing I was trying to show you with that ball on that thing yesterday, that if you get things hot enough, that's what their colors would be. And that's how we know that our yellow sun is in that temperature range. Okay? And we unfortunately can't see the colors that great here on Earth. The atmosphere gets in the way. We talked a little bit about how when the light goes through the atmosphere, it reflects and gets rid of some of the blue light and lets the red light go through. That's why we see that red, blood red lunar eclipse, etc., etc. Actually, there's one tonight, right? So on Earth here, we don't see the colors very well, but I've read and I've heard interviews of astronauts that go into orbit above the atmosphere, and they say looking at the stars there for the first time is like first looking at color TV when you used to watch black and white TV for all your life type thing. So it's very colorful. We don't get to see that same effect. Okay, are we okay with the fact that hot is blue and cooler is red? Now, at this point, we want to really finish this note. There's not much left here. So we want to talk about then the life cycle of the stars. I've already mentioned this when we talked about solar systems. This is what precipitated our great discussion, which now we'll write it down, and we won't worry about that right now. Maybe on Monday is where we'll talk about it. So again, this talks about this nebula. Nebula kind of means a spread out, diffuse, not diverse, but diffuse, spread out, thin, and thin what? Gas and dust. All right? Our star is believed to be a second generation star. That it's been formed by the gas and dust that came from a previous star that was in this region of space. A first generation star would be a star that we believe was formed soon after the Big Bang, the origin of the universe, created out of that original matter that was created then, and we'll talk about the Big Bang on Monday. It doesn't matter what generation it is. There was a bunch of gas and dust hanging around this region of space. Gravity begins to pull it in. I haven't talked about the rotation. It's okay. But remember, if the gas is rotating slightly as it gets pulled in, like the figure skater who pulls his arms in, rotation happens faster. Typically, there is a dense central mass that contains lots of hydrogen gas. If there isn't enough mass there yet, it may not have enough energy, so it's not quite a star yet. It hasn't lit up, so we call it a protostar. That's proto comes before, just before the star, yes. Gravity begins to pull in the gas. Yeah. Yeah. Again, I wrote these myself, which means there's potential for lots of grammatical ugliness. Again, I mentioned some smaller masses can gather in orbit around the center, and those become planets. We've talked about the planets in our particular solar system. And again, just like I said momentarily, just like when you pump up a tire, you squeeze a gas down, things get hot because that energy of the squeezing goes into the particles and they start to move faster. We talked about that in chemistry, right? The kinetic molecular theory. By squeezing all those particles together, they start to bump into each other, they start to move faster, they start to collide with each other. And once they run into each other fast enough, in other words, if they're going hard enough and those protons can run into each other fast enough to overcome the repulsion, and they stick, and it makes helium, then that's the engine. It starts. That's called fusion. And when those reactions kick in, massive amounts of energy are produced, and the star lights up, comes into being. Okay? Well, it's always there, but it becomes a star in that it's now producing its own energy. Okay? And then it continues to gather up gas, cleans everything up in the solar system. Planets gather up all the rocks and dust around them. If there isn't one, maybe an asteroid belt. The star gathers in everything, and then the solar system is running. The machine is running. And that's where we are right now. We're in the Middle Age, all right? Okay? And that star is turning hydrogen into helium, running along. Okay? Let's talk a little bit about what it means to be a middle-aged star. So that's my next one. And then we'll talk about what happens when those stars run out of fuel and what happens at the end of their life. I guess we call it stellar death. Such a morbid thing, but that's what we talk about. Okay. How are we doing? Good? No? Yes? No? Questions? Yep.
Don't stars like die multiple times? Like doesn't it die then form into a smaller one?
Okay, so once we get to the end of the life cycle, we'll talk about the possible endpoints that we believe take place. And you're correct. As I stated at the beginning of this slide, that we believe that our star that is in our solar system is a second generation star.
So then would it get in third?
Will there be a third, et cetera, et cetera? Not likely. We don't believe there will be. And I'll explain why when we get to the end of the life cycle of our particular star, okay? The main reason our star is not believed to create another star in this particular location, it's too small. It doesn't have enough material in it. It doesn't have enough hydrogen in it, so that at the end of its life, there isn't enough hydrogen to create another star like the way it did in this case. So we believe that in this region of space, that when our star is done its life cycle in another 5 billion years, that we will not be left with another star coming in its place because the dust will not contain enough hydrogen in it. Okay? Yes? Let's first talk about the different types of stars and how they die, and then we can talk about that. Yes? Yep? I'm going to just move ahead here. You're talking about a character from Guardians of the Galaxy. And yes, science fiction likes to use spacey names. Yes, I'm going to keep going here. All right, so now listen up. This, and you're not writing this slide, this is the way we categorize stars. It's called an HR diagram, named after two scientists who created it. The H is Hertzberg was his name, and I don't know whether they were colleagues or not. The other guy's name was Russell, last name Russell. So this is called a Hertzberg-Russell diagram. Now let's just take a look at what's on this diagram. This came out of your textbook. It is in it, but I'm not going to ask any questions about this on a test, but I just want us to take a look at it. On the side here, you'll notice it says absolute magnitude. That's that brightness, right? So up here, you'll notice that in the negatives, these are super bright stars. And down here in the positives, they are super dim stars. And then on the bottom, these particular scientists decided to put the temperature, all right? So we've got two things here. We've got the brightness and we've got the temperature, okay? So down here in this corner, you'll notice we've got some really dim, tiny little stars. They're not that exciting. They don't do very exciting things at all. They just have a little bit of fuel in them. They're not producing a lot of energy. They're very dim. In the middle, you can see we've got these yellow, mid-size stars. Again, that's where our sun sits on this graph. And then way up here, you can see that there are stars that we can see that are very hot, and because they're so bright, we assume they're really big, all right? And so we've got these big blue stars. Now, if we graph this, these scientists realized that we get this nice kind of curve, and they called that curve the main sequence. It's just where middle-aged stars hang out, all right? So, on the main sequence, that's where middle-aged stars are. When they end up running out of fuel, they can end up leaving the main sequence and ending up over here. These big guys tend to end up over here, all right? And these little guys tend to end up over there, all right? And I remember in this course, we had to do calculations that then plotted these tracks. So this is where stars go to die, all right, on the graph. So we now know that if we take a look at a star and we take a look at its brightness and we take a look at its color, we can tell whether it's middle age or whether it is on its last legs. In actual fact, it goes to here, and then these actually also jump down to here. It's kind of neat the way they kind of end up. But we use this chart now to look out there, look at the color, and see whether a star is ready to die. This one right here called, some people like to just call it Betelgeuse. There used to be a movie that was called Beetlejuice. So I've heard it called Betelgeuse. It doesn't really matter. This one, we're going to talk about this. It's in the constellation Orion, and it is right on the edge of its life. And in October, it went from being super bright and has started to dim greatly. Since October, some scientists believe that star is ready to go, that it's going to explode, and we might be able to see it. Other astronomers say, just hold on. It could still be 20,000 years. Everyone just wait. But it's getting very dim all of a sudden. Since October, I'll show you a picture of it. So we're really close to the end of this particular star's life. We know it because we can put it on our Hertzberg-Russell diagram, and we can see the light changing, and so it gets very exciting for astronomers. Yep. I'd have to look that one up. It's not close enough that we're going to be in any trouble if it explodes.
Like 6
Oh, you're right, because it takes the light. You bet that could have already happened, and we're just waiting for the light to get to us. Correct. I'm not sure exactly how many light years. You could just do a Google search, it would tell you. Okay, let's talk about these stars. Now, by the way, I've got 1, 2, 3. 3 more slides. Let's talk about small stars. And I need my cheat notes at this point. Can I put what here? What's happening? I've got to have my cheat notes. You guys can start writing. I got to move my notes over here so I can see them. Escape. Bring that over here. Sorry about this. Click. All right, you're in good. $642 light years. Yeah, so 600 light years. So 600 years for that data to come to us. So it could have gone off. You bet. We're waiting. So let's talk about what we end up with after our star runs out of fuel. So first, let's talk about main sequence. What is it on that line? Are we ready for the chart? We got the chart built? Doesn't have to be a chart per se, but I am going to work my way across. Our main sequence star is called a yellow dwarf. Yep, dwarf. It's not very big. And it's yellow. It's a yellow dwarf. And what's happening right now? Well, the word is fusion, but I'm going to say it's burning. The sun isn't burning. It's not like a fire. It doesn't need oxygen. It's squeezing the hydrogen atoms to become helium atoms. Everybody kind of get that? So there's no oxygen out there on the moon. It's not burning like a piece of wood. So I'm going to put in quotes here, burning, all right? B-U-R-N, I apologize, my scribbling. It's not really burning, you get the idea. It's burning H to He. It's squeezing the hydrogen to become helium. Okay, we're okay with that? Doing its regular thing. All right? When the H runs out, all right, what happens is the inner part of the rings, the inner part of the sun, begins to collapse in so that the He can squeeze into bigger things. But the outer layer starts to escape the gravity. It gets out there. So we end up with something called a red giant. It's going to become so giant that the outer surface of the star will encompass our orbit. It will go out to just about the asteroid belt. That's how big the star will become. So we will be existing in the interior of the star. We'll all be dead by then. That's in 5 billion years. You don't have to lose any sleep. It's not going to happen tomorrow. All right? But it's going to expand. All right? In this case, H runs out. The hydrogen runs out. Alternative nuclear reactions start happening, but it's run out of fuel. H runs out. And the outer layer expands. And it gets cooler as it expands out. So you've got kind of a piece of a star on the inside burning away, but the outer layer now expands. That convection zone gets really big. All right. Death. death, we have what's called a white dwarf. All right? It's even smaller than the yellow dwarf. Don't mind that. That's Miss Jackson. She's loud. She's pretending to run battles in history. White dwarf. The outer layer drifts away. The outer layer drifts away and it becomes so thin that you can't even see it anymore. All right? There is a small, hot Fe core. What do I mean by Fe? It's iron. So, our star will become a hot ball of iron hanging there in space. Yeah, we'll all be dead. Okay? Eventually, just like any other hot object that doesn't have any heat in it, what's going to happen to that white hot piece of iron? What happens to any hot piece of iron in the shop? It cools and becomes a hunk of iron, dark. In the end, it becomes a brown dwarf. Essentially, a hunk of iron in the position at which the star was. Why is it called brown? Because it's not giving off any light, not giving off light. It is the most unspectacular way in which a star can die. Boring. Left with a hunk of iron sitting there in space. Okay? Let's now talk about larger stars. Now you'll notice I've got medium stars, about 10 to 30. What do I mean by M with that symbol? What do I mean by that? Yep. What does the letter M stand for in our study of this stuff? Nope. Yep. Nope. Yep. This is super important. I'm going to go back and define it on the other one. No, you didn't. You tried to be loud. This is mass. Mass of the sun. I don't care how bored you are. I'm not talking to you. I'm talking to everyone in this room. This is information I have to give you, so I'm going to do it. If you could be respectful and let me get through it, it would be great. So, that capital M with that dot means mass of the sun. Sometimes we call it solar masses. So I'm talking for our star, things that are about the same as our star, or 5 times the mass of our star. Does that make sense now? Okay. So let's now go to the next one. We're talking about bigger stars. So now I'm talking about 10 to 30 solar masses. 10 to 30 of our star's mass squeeze into one. Yep. That means the sun. That stands for the sun. That's why M, with that symbol, means masses of the sun. So 30 sun masses. Okay, so now we're talking medium. Their main sequence, and I don't have the main sequence for this one. It's not a red giant. It's not a red supergiant. I don't have the name for this. I'm going to leave that blank. But these, and I'm going to go and find it. These ones, though, they burn hot. Okay? They burn hot and fast. All right? So larger stars do not last as long as our star because they're heavier and they burn hot and fast. All right? I said that our star is about 5 billion. These things last only a few million years. All right? They don't last very long. Million years. Yeah. Yeah. It actually isn't. Because again, if you think about evolution of plants and animals on this planet, it's in the millions of years. So that if there's a planet around that star, and we hope that evolution were to kick in for life around that star, it's never going to happen. It doesn't have enough time. That star is going to die and explode before anything kicks into gear. So it is a short period of time compared to the life of other objects. Okay, this one, when it becomes old, becomes a super red giant. Super simply means it's huge. It's way up there in the corner of that Hertzsprung-Russell diagram. All right? That Betelgeuse star would be this one. Okay? Or the next. It's hard to tell. And again, what's happening there? Again, fuel runs out. The fuel runs out. The H runs out very quickly. And it swells and becomes very large. And I know it's really poor descriptors, but it gets bigger than the previous ones, okay, than our star. Now, death. Again, the outer part swells and leaves away, but there's so much material in that larger star that when the fuel runs out, it collapses so fast that all the material that runs into each other at the center and it bounces back out. So gravity pulls it in so fast that all those particles hit each other and then they explode back out. An explosion because of the super collapse of that star. And it produces what we call a supernova. Our star will not produce a supernova. It's not big enough. So as it runs out of fuel, that collapsing, gravity wins, pulls it in, and it smashes in and then blows out. Supernova. Strong gravity causes collapse. All right. E on the end of collapse? I'm not sure. Causes it to collapse. As it collapses, it causes a rebound. It bounces off of the center, causes a rebound. The rebound causes an explosion. All right? Okay. It doesn't explode all the material. There's still a core. And that core is called a neutron star. And we're getting to the point where I'd really like to talk more about neutron stars. The gravity is so great, still left in this material, that all the atoms that are in that material, the gravity squeezes the electrons into the protons and turns them into neutrons. That's just fun to think about. What's the charge on an electron? Yep. What's the charge on a proton? If I were to squeeze the positive and the negative of an electron together, what charge would I get? Yep, neutral. And that's exactly what happens. Gravity is so great that it squeezes the electrons in the orbits right into the nucleus, where then the electrons combined with the protons to make a massive star made up of only neutrons. Yes? The math works out. Trust me. The math will work out. There won't be double the amount of protons and neutrons, because there will be the electrons that are the same number as the protons, and they're going to get squeezed into each other to make the neutrons. Okay? So, let me add this down. Gravity pushes the electrons, E minus, into the protons to form N0 neutrons. The density of a neutron star is the density of a nucleus. It's super small with lots of mass in it. If you were to take a sugar cube of a neutron star, you would have the mass of, in my textbook it said, Mount Everest. Because it's so densely packed, the materials. It's as dense as a nucleus. It can even be considered its own nucleus with no protons, with a massive number of neutrons. It literally is a massive stellar nucleus. Yes? That would be bad.
Well, I know it would be bad, but what would happen?
Well, it wouldn't crash into the Earth, because the Earth would crash into it, because its gravity would dominate, and the Earth would be a tiny little speck of nothing compared to it, and would get sucked into it. And once it got caught into it, our electrons would be squished into our protons, and we would simply become part of the neutron star.
So it's like a...
Well, yeah. Any, stellar collision with Earth is bad. No, it's just before a black hole. There's the next step. If we have more mass, okay, then the gravity becomes so great on that structure, even the neutrons can't hold each other apart, and gravity wins, and it squeezes all the mass into at the tiniest point you can imagine. That's even not tiny enough. That's a black hole. That's the next step.
Okay, and who figured this out?
It's a theory based on the physics, the laws of physics that we know.
Okay.
I'll bring my textbook on Monday, and I had to do math in that course on what mass would then result. Oh yeah, it was the hardest course I ever took in university. It was first year university. I wish I had taken it at the end of university. I would have understood more of it. It was an awesome course, but the math was crazy. It was awesome. Yes. Let me finish this, and then I'll get to that, because this, I believe, is my last slide. Is it my last slide? I think so. Yeah. Oh, there's just pictures. Just pictures. Let's finish this. Main sequence. A blue supergiant. These are bigger. These are hotter. They last even less. They burn out like crazy. They're like flashes in a pan, right? It's like lighting a match. Then it's done, right? And again, burns hot and fast. Few million years. Super red giant. So you'll notice it's progressing kind of like the last one, right? It expands a lot. So this is old age, right? Remember that outer shell is taking off. Again, death, supernova. Just like the last one. Collapses in hard, rebound, explodes, and then there's some material sitting there. So this is the same as the other one, right, as the previous. Remains black hole. H, not the entire. A black hole. A black hole has so much matter that not only do the electrons get squeezed into the protons to become neutrons, but even that neutron up against a neutron is not enough to keep gravity from squeezing that matter to higher and higher densities. And then it begins a collapse that cannot stop. Because if you have the strongest particle in matter, which is a proton or a neutron, and you are now squeezing it down, there's nothing in nature that can stop that. So it squeezes it to what we call a singularity, a single point in space. If I were to take my bowl, you know, my bowl that I put the marbles around, you could imagine as if instead of it stopping at that flat spot, that it just keeps going deeper and deeper and deeper, infinitely deep, down to one point in space. So it creates super strong gravity, super strong gravity. The gravity is the same, it's just there's so much mass that it squeezes it in. Squishes all matter, do I want to use the term singularity, to a single point. To a single point. That single point we call a singularity. I'm not even going to put it on there. And it's a black hole because not even light can escape. The reason light can't escape, if we do the math, remember escape velocity? What was the escape velocity for the Earth again? Yeah? I think it was 11 kilometers per second, but that's okay. And then it was 20-something for the sun or 40-something for the sun. The escape velocity for a black hole is the speed of light. 3 times 10 to the 8th meters per second. In other words, not even light is going fast enough to get itself out of the hole. That's why it looks black. Okay? All right? Now, I'm just going to stop here. Let me just show you a few things, and you asked me a question about a black hole, right? Yeah. Sorry? How heavy would it be, right? Okay. Let me just show you this. This is a picture of the Betelgeuse star, taking into account its radius. This is what we see. This is Saturn's orbit, and this is Jupiter's orbit. So this is in its super red giant phase. It's huge. If it were our star, our super giant or our red giant would get out to about there, just beyond Mars. Okay? This is the one that's been dimming since October. So is it the beginning of the collapse? We can't see enough detail. We don't know that. Some scientists think it might be. One last thing. This picture here, oh no, that's a nebula. That's what's left after a supernova. That's the outer shell that's kind of spread out. And this last one here, this is the first picture that humans have ever taken of a black hole. Up to this past summer, we've only theorized what a black hole would look like. This is a picture of a black hole. This darkened area in the middle is what we believe to be that area where light can't escape. This ring around it is believed to be matter falling into it maybe from a supernova, that as it falls towards it, it's getting squished and getting really hot. So it glows with a little bit of red light. And then once that matter gets sucked in, you can't see it anymore. So this is what we believe is called an accretion disk. It's acquiring material from around it, and it's sucking matter in. All right? Question? Sure it can. Anything that gets close enough, just like my orbital toy, can get pulled into that, and then it's in the black hole, never to come out. Nothing can come out of a black hole. Now, Stephen Hawking predicted that energy can escape very slowly. And we believe that black holes can actually eventually evaporate, which is kind of neat. But that's really some high-level stuff. Yes? Oh, yeah, it's way out there. It's definitely not in our solar system. We don't have to worry about that. If you want to be freaked out, some astronomers believe that there are rogue black holes that have sucked up all the stuff around it so we can't see it, that could be traveling in our galaxy, that could be just out there, just outside of our solar system. And if it decides to take the right turn, we would be in trouble. I choose not to believe that. What's that? Am I? Rob's like, oh, rogue black holes. We can't even see them coming. Okay, that's a good question. That's a great question. What would happen if a person got sucked into a black hole? I'm gonna stop my video here for a minute.